Cool. Okay. We are live. How do I share links? I have no idea what I'm doing. Once again. Hold on. While people are coming, I want to figure out how to share links. Because that seems important. How does one share links to a live stream? Is it that link? See, I don't think it's that link. Because if I go here, yeah, that's not a video link. I have no idea what I'm doing. Settings. Man, I figured this out the last time and I completely forgot. How do you link a stream? I got this. I can go to my channel, which apparently doesn't exist. Yikes, okay. What if I just go, oh, that's not what I want. Okay, well, darn it. I'm gonna figure this out. Aww. Ah, there we go. Share. Copy a link. Alright. I'm live. Okay, that's a thing. And if I go here, there we go. Okay. Oh, that's not what I want. I don't want to do that. All right. Technology is so complicated. All right, cool. The data has been done. Let's talk about ink. So, nice. So ink is a programming language that I made. And it looks like this. So I can start up the REPL. You can add numbers. You can divide numbers. You can assign numbers to variables. And then a plus b is 50. You have strings. And then you can add strings together. And you can have functions. Functions kind of look like JavaScript functions, where you can say like 4 plus 5, and then you can run that. So this is the REPL. It's a language called ink. And I wanted to talk about how this works and sort of what goes into making your own programming language. If you're actually curious about the code, you can go to linux.zone/ink or my GitHub page. And there's a lot more information about here. My website runs in this language, as does a bunch of other things like Mandelbrot set renderer, things like that. For now, let's just talk about making programming languages. So, okay. So programming languages, if you haven't studied it, feels kind of daunting. But the process of going from a program, which is just a text file, to like something running, is really just a pipeline of a bunch of different stages that happen. More sophisticated programs have a lot more of those stages, like Python or Ruby have a bunch of these different stages. JavaScript is famously very complicated. Ink is very simple. So Ink is written in Go. It's about 4,000 or 5,000 lines of Go, give or take. And Ink has 3 different stages that happen in running an Ink program. So those 3 steps are lex, or tokenize, parse, and then execute. And they're a pipeline where you start with just a bunch of characters, a bunch of letters, like a text file. And then you take that text file, and then you turn them into tokens, which are like meaningful chunks of text. So an example of a token is like the right parenthesis, or the variable name a, or the string what, or the number 34.5. These are all like valid chunks of text that are like independently meaningful. So once you have that token, the list of tokens, the parse step takes that token, the list of tokens, and turns it into a syntax tree. In more sophisticated interpreter or compiler pipelines, you will have multiple different kinds of syntax trees that go from like very human readable to very machine friendly. Ink has just one type of syntax tree, and it's just the canonical like syntax tree. And if you're confused about what the syntax tree is, we're going to see that in a little bit. And the last step is to take a syntax tree, which is just this data structure that represents the syntax of Ink, and then there's a program or a function that you can call on that to actually run the contents of that syntax tree. So that's all very confusing and doesn't make sense. Let's actually try to figure out what's going on. So when I do Ink REPL, I can just run the program, but Ink also has this debug switch. So we're going to debug the lexer. And that means that it's going to look at the program that I type in, and it's going to show us the output of the lexing step, which is taking a bunch of characters and turning it into a bunch of meaningful chunks of text. So if I type in 3, there's actually 2 different tokens that are contained in this program that just outputs 3. The first is, no, that's not what I wanted to do. The first is the number 3. So we see that there's this number literal 3, and the number literal just means it literally represents the value of the number 3. And this little thing in the bracket tells you where in the program that occurred, which is like nice for debugging. And then there's this fake token that's comma, that's kind of like a semicolon in most languages, that's inserted after the end of every program. So pretend that doesn't really exist, it's kind of auto-inserted. But this program has one valid token, which is the number literal 3. If we do 3 plus 3.14, then there's 4 different characters. There's 3, and then a period, and then a 1, and then a 4. But really, it's just one semantic thing, right? It's still like one number. And so the lexer looks at this and says, well, there's 4 characters, but it's still just one number value, just one number literal, and the number literal is 3.14. And so the tokenizer, the lexer, takes the string 3.14, and then turns it into, okay, well, there's this first token, which is 3.14, the number. The second token is this like fake auto-inserted comma. Let's do something a little more complicated. If we do like 1 plus 2 plus 10, there's a lot more tokens in this one. There is the number literal 1, which is the first thing. The second thing, there's a plus sign. Spaces don't really mean a lot in Ink, so spaces are ignored by the tokenizer. It just looks at the space character and says, okay, that just means it's the end of whatever was last. So the next token is this plus sign, which is just a plus operator. After that, we have another number that's 2, and then another plus line, and then another number that's 10, and then a comma to end the program. Makes sense? If we do something like how plus space plus ru, then we see another kind of token, which is a string literal. Just represents like a string value. And the Lexer looked at this and said, okay, it's a quote followed by a bunch of letters followed by another quote. That means this is like a chunk of characters that represents a piece of text. And then a plus sign, and then another quoted piece of string, which is the empty the space character. And then you'll see that with every single token, I'm also keeping track of where in the initial program that token occurred. So when there's an error, I can be like, hey, the error is actually in like this part of the program. Another interesting example to look at may be a function. So we can define a function as something that takes no arguments and outputs true. Okay, so this is a little bit more complicated. We see this new type of token called an identifier. An identifier is like a variable name or a dictionary key or a parameter. Those are all identifiers. They're like slots that you can put values into. So this is an identifier called func. And then we have this assign operator, which is kind of like the equal sign in most languages. We have an open parenthesis, which is its own token, a closed parenthesis, which is its own token. These are just distinct symbols that each mean their own thing. We have the arrow operator, which is telling you that this is a function that I'm talking about. This true literal, which is like a Boolean value. And then, again, a comma to end the program. So that's kind of what the Lexer does. How does it actually work? Well, if we look at lexer.go, the good place to start is this block of constants. So this is Go code, and you don't really need to know Go to understand it, but basically I have a type that's just a token, and there's all the different types of tokens that that can exist in an int program. I kind of have outlined here. So a separator is just a comma, and then there's a binary expression like plus. There's a match expression, which is kind of like an if-else. There's an identifier, which we saw. There's a function call. There's a number, a string, an object, a list. A list is like if you do 1, 2, 3, 4, that's a list. A function literal. There's a true and a false. And a bunch of other kind of operations that you can do, like math operations, like divide, modulus, greater than, less than, etc., etc. So if we want to do a little bit more math, because I think that's kind of interesting, if we do like, is 3 greater than -1 plus 1? I just realized I'm in there. Plus 1. There's a bunch of stuff, a bunch of tokens in this program. The first one is the number literal 3, and then we have the greater than operator, a negative sign, a number literal, a plus sign, a number literal. So this is like a unarray operator because it only affects the first one, the first number 1. This is a binary operator because it affects both the left side and the right side. So these are just a bunch of symbols, and what the Lexer does is it goes through in like a giant while loop and tries to figure out, divide this list of characters into meaningful chunks of characters that are each its like own symbol. Is there anything else that's kind of interesting? So this is the main function that takes a stream of characters and it returns a list of tokens. Most of this isn't really relevant, but you can see, for example, there's this giant for loop. In this for loop, we have a bunch of like switch cases. So like if their character is a quote, then we check if it's in a string, blah, 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 blah. Other fun stuff. This is a little more interesting. So for example, if it's a plus sign that is the character that we're currently on, then we tack on an add operator. If it's a multiply sign, we tack on a multiply operator. And this just goes in a giant while loop that loops through each character in a string. So if we have like 3 plus 4, the characters in that are 3 space plus space 4 end of string. So it'll do a while loop that looks at 3, it's a number, space, we don't care about that, plus, go through, that's a plus sign, commit that, and so on until we have this like list of tokens. Hopefully that kind of makes sense. And there's some like special case code to handle funky cases, but again, like parentheses, open bracket, close bracket, things like that. There's a bit of special case code to handle like automatically inserting that comma, but that's not super relevant here. Cool. So that's the lexer. And if we can actually run a complete Inc program and look at sort of a meaningful chunk of lexer output. So if we look at like, so this is an Inc program that just calculates the 20th Fibonacci number. It's like a small Inc program. If you run this with the lexer debugger turned on, it errors because I got the flag order wrong. Okay, so it spit out the error or the answer at the end, which is cool. But these are all of the tokens that exist in this program. The very first character in line 3, column 1, is an identifier called log, blah, 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 blah. These are all the different types of tokens. And the lexer, as we outlined here, just takes a list of characters and just gives you a list of tokens. So it's a little more interesting. The list of tokens is a little more meaningful than just a giant string of characters. But it's still not good enough where we can give it to another function to just run the program. So the second part of this pipeline is we have to parse the list of tokens into something a little bit more meaningful. To understand what's going on there, we have to take a look at the language a little more closely. So let's say, okay, I'll just show you the parser, lexer output and parser output. So this time I'm going to turn on both switches. So let's say we have the program 1 plus 2. So the debug lex, things that say debug lex are the lexer output, things that say debug parse is the parser output. So the lexer found 4 different tokens in this program 1 plus 2. There's the number 1, there's a plus sign, and then there's a number 2. And then a comma at the end, which never really matters. And then, so what the parser tries to do is it tries to take this list of tokens and group them in a way that makes sense. In this case, the grouping that makes sense is that 1 plus sign 2 can be grouped into some kind of a binary operation, where the left side of the operation is 1, the right side of the operation is 2, and the actual operator is plus. So the parser took this list of tokens and output a binary operation where the left side is number 1, the right side is number 2, and the operator is plus. If we do something a little more complicated, like 1 plus 2 plus 3, well, then we have to figure out how to group these, right? So binary operators can only operate on something on the left side and something on the right side. So in this case, we want to group it so that like 1 plus 2 happens first, and then outside of that group, 1 plus 2 is added to the number 3. So we get 5 tokens, 1 plus sign 2 plus sign 3, but the output syntax tree is, well, we first see the binary like operation, number 1 plus number 2, and then there is a bigger binary operation that is the result of this entire thing added to another number. So there's like 2 layers of binary operations going on. It's kind of like if we did 1 plus 2 plus 3. The output here is a little bit more complicated, but essentially we're getting this similar type of output. If we do like, okay, another good example is, so in Inc we have this thing called a match operator. So a match operator is like true and false. So it looks like this. So let's say A is like 10. And if we do is A equal to 10, is true, is A equal to 11, it's false. Okay. So a match is kind of like an overpowered if-else. So So we can say match A to, if A is 10, then output A was 10. If A is 20, output A was 20. And then if A is none of the above, then output whack. So that's what a match expression looks like. And in this case, A was 10, so, you know. But let's look at this like simple thing. So this is a really simple match expression. It just says, if A is 10, then output was 10, otherwise do nothing. So if we run something like that with the lexer and parser on, if A is 10, okay, so what are the tokens in this little program? Well, we have the variable A. Oh, it errored because A is not defined. Okay, well, if A is 10, was 10. Okay, so we have the variable A, and then we have this like match symbol. We have a left brace, number 10, the right arrow, string was 10, and then auto-inserted comma, left brace auto-inserted comma. The last three aren't super-important. But if we look at the syntax tree that was generated, how these tokens were grouped together, it's grouped together like this. Well, the parser looked at this and said, it looks like because it's an identifier followed by this match thing, it looks like the entire thing that is the program is a match expression. We're matching on identifier A to, in this case, one clause, which is like the result of the match. If it's 10, then output was 10. So the parser at a high level takes a list of tokens and tries to organize it into some like structured expression. Whether that structured expression is like a function or a binary expression or just a number, there's a bunch of different cases. So at a high level, that's what the parser does. So a parser takes a bunch of tokens and outputs a syntax tree. And a syntax tree is just a grouping of tokens into expressions that make sense. And if we look at the parser, because it's a syntax tree, each thing in a tree is called a node, which is why there's this node interface. Whoa, what did I do there? This interface. The important bit are there all these different kinds of nodes. So for example, when we say, when we say 3 plus 2 plus 4 plus 10, it puts out, well, it's a binary operation on 2 and 4 with a plus sign in between. That's a binary expression. And the binary expression is like a type of an expression, which is a node on the syntax tree, which all that means is like it's a type of expression that the parser knows about. So a binary expression contains an operator, like plus or minus or multiply. It contains a left operand, which in this case is 2, and then a right operand, which in this case is 4, and then a position, which is like where in the file is it, which isn't super important. So binary expression is pretty simple. Another kind of expression is if we define a function like that, we can call my func, and it outputs 10. But when we call my func, this is a specific kind of expression. This kind of expression, an identifier followed by 2 parentheses, means that this is a function call. We're calling the function myfunc. So this is a specific type of expression, and specifically, it's a function call expression. A function call is really simple. It's what function do we need to call, which in turn is another expression, and what arguments does it have. So in this case, it had no arguments, and the function was just the identifier myfunc. So you may ask, like, why isn't this just like identifier node? Like, why isn't that true? Well, what if we do like, let's say we have a list of functions. So like, the first is a function that outputs 1. The second is a function that outputs 2. Okay. I want to assign that to something. List of funcs. Okay, so that's a list of functions. So list of funcs, 0th, oh. I forgot my syntax. The 0th thing is a function, and the first thing is a function, and they output different things. If we want to call the 0th thing in the list as a function, we have to do like that, where this part is an expression that evaluates to whatever that function is. So it can't just be like a variable name. It has to be the function part of a function call has to be able to take an expression. If that last bit didn't make a lot of sense, it's not super important. Don't worry about it. But these have to be fairly generic because of the way the programming language works. Here's a match expression that we looked at before. This is an identifier node. An identifier node is just a variable name. So like my func. This is an identifier node. It's an identifier, which means it's just a variable name, and the variable name is my func. If we do like A is 10, B is 2, and then we do A plus B, it's a binary operation between one node, which is an identifier A, added to another node, which is an identifier B. So you see kind of how these different types of expressions like build on each other and compose on each other to make more complex expressions. Here's a node for a number literal, like 2 or 3.14. Here's one for string literal. Here's one for booleans, which is true or false. We also have objects in the language. So these are nodes for an object. An interesting thing to look at may be like, okay, let's say we're looking at an object. So in Ink, an object looks like this. Key 1, first value, key 2, second. So it looks like JavaScript objects or Python dictionaries or something like that. The way that this breaks down in syntax, in the syntax tree, is it's actually an object that contains both keys and values, right? So really, an object is just a list of key value pairs, where this object contains 2 key value pairs. The first key value pair is a pair of key 1 to the string first value 1, and the second key value pair is key 2 mapped to second. So the syntax tree, well, the parser looks at this and says, okay, this is one giant object. The object contains 2 object entries, which are these expressions. An object entry describes a key and a value. So the first object entry contains the identifier key1, which points to the string first value. The second object entry contains the identifier key2, which points to the string second. Does that make sense? I have no idea if that makes sense. Hopefully that makes sense. Cool. And match expressions kind of works similar way, where there's like clauses that you have to match. A function literal is kind of interesting. So a function literal, what's a function literal? A function literal is when you're like, my func takes a number and then returns the number squared. If I can type, God. Ugh. Okay, so we can say my func, actually let's name this what it is. It's a function called square, returns n times n. Okay, so if I do square of 3, it returns 9. If I do square of negative 14, it returns negative 196, which I know off the top of my head. Just saying. Okay, so this is a function call. It calls a function that is the identifier square, so it calls a function called square, with the argument being, in this case the argument is number 3, in this case the argument is negative of the number 14. But if we look at how this function is defined, like this thing is also its own thing. Like this is a type of expression. It's specifically a function literal. So on the left side of this, we have, so the parser says this whole thing is actually a binary expression. It's an expression of like the left thing is the name to assign the thing to, and the right thing is the value of the thing that it's being assigned to. So it's a binary expression that is an assignment. The left side of the assignment is the variable name square. That's the function name that we're going to assign to. And the right side is a function literal, which is a description of a function. And the function takes an identifier n as an argument, and it returns the result of a binary expression, which is n times n. And things just build on this. So, so the way that the actual like parser works, so this is the parser, it takes a stream of tokens and it outputs a stream of nodes. And most of this is kind of Go finagling. There's actually some really interesting stuff here around like order of operations and things like that, but maybe I'll go into those later. But the heart of the parser is this thing. So in most languages, inside a parser, you will run into the concept of this thing called an atom. And different languages use it in different ways. I know Python has a concept of an atom. An atom is like a compact, like a small expression that is like its own thing. So in int, an atom is anything that is like a single value. Like 3 plus 4 is not an atom. It's like 3 is its own atom, 4 is its own atom. But like, what's an example? Like -2 is an atom. Right. And so this is kind of the crux of everything. There's also a parse expression, which parses like larger expressions. And if you're familiar with the concept of mutual recursion, these functions that know how to parse different things mutually recurse on each other to parse things inside each other. So if we have like 1 plus 2 plus 3, well, to parse this thing, we have to be able to parse, you start here, and you parse 1, and you parse the plus sign, and then you get to another expression, and you're like, okay, well, we need to like recursively call parse expression on myself again to parse the thing that's inside and then come back out. Maybe that's not super important. But that is the parser. So a parser takes a list of tokens and outputs a syntax tree, and all a syntax tree is just like a logical grouping of different tokens so that it makes sense. So both of those things are pretty conceptually straightforward. It takes one type of symbols and turns it into a list of another type of symbols. But you're still just left with this like data structure. How do you actually make it run? Well, this is where compilers and interpreters differ. So compilers will distill down syntax trees into more and more abstract syntax trees and then generate a list of machine code. An interpreter just runs that code. So Go is nice because Go has a lot of nice facilities built in. So in Ink, everything that is in this third step of executing the syntax tree into a running program lives inside a Go file called eval.go. And the way that eval works is it takes a syntax tree and evaluates it. For example, if we have 1 plus 2 plus 3, it looks at the syntax tree and just kind of evaluates everything from bottom up. So the first thing that it looks at is, okay, what's the innermost value? The innermost value is like number 1. Number 1, that's like very trivial. It just means the number integer 1. Same with number 2. And then if you go up the tree 1 level, we have to compute this binary expression 1 added to 2. Well, what's that? That's 3. And then if you go up one other level, you have to figure out, okay, what's this thing? It's also the number 3. And then you binary add again the number 3 from the first thing, add it to the number 3 from the second thing, and then you get 6. So it looks at the syntax tree and kind of just bottom-up evaluates it. So again, it's kind of a recursive process. And a type in the Ink interpreter that's important in this step is this thing called a value. A value is really just like, it represents a value like a string or a number or a function. There's all kinds of values. There's a number value, as we see down here. There's a function value. There is an object value, or it's called a composite value. There's a null value. A null value is just that. Kind of like in Lisp. Actually, not at all like in Lisp. There's a Boolean value. And the way that the interpreter goes about interpreting it is it looks at the lowermost, the innermost things in the syntax tree, the groupings, and then sort of evaluates it bottom up. So I want to try to find a piece of this that's actually kind of interesting. Okay. So, oh wow, I did not mean to zoom out that much. Okay. Let's look at how a binary expression is evaluated. So if we do like 1 plus 2, this is a binary expression. It has a left side, a symbol, and a right side. How do you actually execute that? Well, conceptually, it's really simple. This is a plus sign, so you add the number on the left and the right. But we could also do this. We could also say like A plus B. This is also a valid binary expression, but this time it's string on the left side and the string on the right side. And if we try to add a string to a number, we get an error. So we have to handle all of these cases. So when we want to evaluate a binary expression, like this, so n is the variable here. N is the variable here that represents the binary expression node. Well, in this case, it's a plus sign, so we have to go down to where we use the add op. So we switch on, after we do some like baseline checks, we do a switch case on the operator, which is the symbol in the middle of the binary expression. The first case we check for is an add operation. If it is a binary expression that is an adding operation, then we have to make another decision. Is it a number add, or is it a string add, or is it a Boolean add? Well, in this case, 1 plus 2, it's a number add, so we go down here. If it's a number on the left side, we do a check to see if it's a number on the right side. That's what this if case is for. If it is, we return the value left plus right. Simple enough. Same thing for string. It's a little bit complicated, more involved because of the way that strings and byte slices work in Ink. But conceptually, you add the string to the left to the string to the right, and if it's like a string plus a number, then we throw an error. So you'll see that, for example, if it's like 1 plus a, or 1 plus an empty string, I guess, it'll hit this case because the left side is a number, but then when we do this check, the right side is not a number. So we're not going to return here, we're just going to come all the way down here. And in that case, we throw a runtime error, which says that values, left thing and right thing, do not support addition, which is true, which is the error that we got in this little thing. Same thing with a subtraction operation, same thing with a multiply, divide. All the binary expressions have this kind of check. This is kind of a giant ugly function, but whatever. So that kind of makes sense. Another thing that's interesting in this execute step is when you assign variables to values, or when you assign values to variables. Hello, there are people watching. Look at that. Yeah, Ink is written in Go. Also, this live stream will be uploaded afterwards as a normal video, so you can go watch it if you are super bored. But yes. So, okay. So that kind of explains that that kind of explains how really simple expressions like 1 plus 2 gets computed. But what if we like assign a value? That didn't work. If we say like x is 3, and then we do x times x, like we have to store the value of x somewhere. So where does that get stored? So for that, we have to have the concept of a stack frame. So a stack frame, if you don't know what it is, it's just a table where it stores like a list of variable names to the values they correspond to, right? And depending on the language, stack frames can get created inside functions. So for example, if we here x is just 3, but if we have define a function that takes an argument x and returns x times x, we can call func on like 10, and instead of saying 9, it'll say 100, because x inside this function means something different than x outside of this function. So to get a better understanding of that, we can run it with yet another debug flag. I think it's actually just dump. So so if we do a dump right now, a lot of these are just built-in functions. Like, what's one here? Like the floor function is a built-in native function. Or like the string conversion function is a built-in native function where like you can do string 10 and it outputs 10. Let me start this over. This is really annoying. So like if you do string 10, it'll convert the number to a string. So this is the current image of the stack frame. We haven't entered any function yet. This is like all of the variables that Ink knows about right now. If we say x equals like 100, and we dump the stack frame again, we have a new value. We have the stack frame now knows that the variable x corresponds to the value 100. If we say y is equal to 100, then we know that x is 100, y is 100. What if we assign it to a function? Well, if we do like my func is takes a and b, and then returns 2 times a times b, then Ink knows about somewhere in here. Yeah, it knows that the variable my func points to a function that is just this syntax tree. Internally, function values are kept remembered inside the Ink interpreter as just a pointer to where it is in the syntax tree. So cool. So now we can use x, y, and my func. And these are all kept inside a stack frame. If you call another function, so for example, if we do my func, if we call it on like 1 and 2, then it returns a number. When we call another function, it opens inside of itself its own stack frame. So the more functions you call, each function invocation like opens its own world where variables can have different meanings. So if we look at the evaler, you'll notice that, for example, when we go to eval binary expression node, so this is what we were looking at before, evaluating a binary expression. And when we evaluate it, we don't just look at the actual expression itself, because what if the expression references a variable that's in the stack frame, right? So we also, eval also gets passed in a pointer to what stack frame is the current stack frame that we're looking at, and then this allow func is something that I'll get to way later. But every time we evaluate something, we also have to know what frame we're currently looking at to be able to look up variable names. And then when we actually, so exec is the master function that like starts evaluating an entire Ink program. This is actually where you see all of the pieces fit together. So if you look at the README, this is a complete Go program using the Ink API. Actually, I'm not going to talk about this. That's kind of dumb. But you can give exec a list of like a file, then exec will like figure out how to run the inc program. The way that it does it, it first tokenizes, then it parses, and then it runs this eval thing, which is up here. I realize this is more confusing than I meant it to be. But I'll just finish my train of thought. The way that inc evaluates a whole program is through this function, where it goes through all of the nodes in the syntax tree grouping list, and then for each node in this like list of nodes, it tries to evaluate it with the same frame every time. So that's kind of how that runs. So if we look at debug, no, what are my flags? Oh, it's verbose. Okay, if we run it verbosely, let's say we do like a is equal to 1 plus 2. That's a program. Well, we can see all of the steps in how the interpreter looks at this program and figures out what's going on. Okay, questions. Sam asks, actually that's not a question, go away. Sahil asks, do all languages use stack frames? I don't want to make any sweeping generalizations, but most of the ones that you're used to probably have the concept of a stack frame. Implementations differ, obviously, for different languages. Compiled languages look at it a little differently. This is like the most naive implementation of a stack frame, which is like, it's a thing that exists inside the interpreter. For lower level languages, stack frames are like chunks of memory. So there'll be like a chunk of memory dedicated to storing the stack of a single function call. The concept exists in virtually all programming languages. How it's implemented in the interpreter and the compiler is obviously different. And because it's like such an often used thing, the performance characteristics of that implementation has a lot to do with how the language itself runs. Hopefully that answers a question. But yeah, for most languages there's like something that is a table of variable names to values, basically. Okay, so when we run this inc program, first the lexer comes in, and the lexer tries to turn this list of characters into a list of tokens. The tokens are the variable a, assignment, the number 1, the plus sign, the number 2, and then the end of the program. The parser looks at this and says, well, this is a binary expression. This whole thing is a binary expression. Specifically, it's an assignment expression. It is assigning to the identifier a the result of whatever this thing is. Now this thing is another binary expression that's nested inside of the larger binary expression. The smaller one is an add operation between the numbers 1 and the number and 2. So this is the syntax tree that we end up with. And then when we actually run it, we end up with the stack frame, which somewhere in it, yeah, a is now mapped to the value 3, because the executor, the eval function, looked at this thing, added 1 and 2, got 3, and then it assigned the value 3 to the slot A in the stack frame, and it got slotted into the stack frame. And it also returned the value 3 here. So that's a general high-level overview of how the interpreter works. So these are all the files. You can go look at it on GitHub. If you what's left is like the command line utility that ties it all together. The REPL that I keep using is really just a giant loop where like it's an infinite loop where it executes the input and then it like logs the output, but that's not super important. I don't know what that question was, but apparently it's been resolved. If not, say it again. But cool. I think that's kind of all I wanted to talk about. There's there's a couple other sort of really niche interesting things, but I think I'm going to cover them in a separate thing. But yeah, another interesting thing is how I got syntax highlighting. So if you go to this is the file server that serves my website, it's written in Ink, and you'll notice that inside Vim, I have syntax highlighting for my language. How do you do that? Well, so if you haven't written a Vim extension before, Vim has a syntax for defining how to syntax highlight a new language. So this is ink.vim. It's a syntax highlighting file for Vim for Ink. So you just define a new file type, and then you define all the different tokens that Vim might encounter and how to highlight them. So this is like Vim specific thing, but for example, these are all predefined functions that are keywords. These are all the different operators that Ink uses. The negative sign, plus, minus, multiply, divide, mod, things like that. So for example here, we're saying match all of these symbols and then highlight them as an operator. But this arrow operator here, highlight that as a function. There's a couple of other things, like parentheses and things like that. But that's how I get syntax highlighting inside Vim. Yeah. That is indeed the language. I feel like that was pretty rushed, but I think I covered everything. If there were parts that were particularly confusing, let me know in the chat, and I can try to talk about it a little more in depth. But that's really interpreters are not that complicated. They're pretty simple. This is the simplest version of an interpreter. You can't really get any simpler than this unless you do some really funky computer science magic. More advanced, I guess I could talk about how I might make this faster. So a lot of production-ready interpreted languages will have a couple extra steps in this pipeline. So one extra step in this pipeline might be to have an optimization pass down here, where it takes a syntax tree and then outputs an abstract syntax tree. So things that might happen in this step are if you have a variable that you can verify that it's not being used, toss it out. Or if you have an expression that you can simplify, simplify it, things like that. Or sometimes it's about consolidating multiple different kinds of operations into a single kind of operation. Like if you have an exponent operator, maybe you turn that into a function call, something like that. Or it may even just turn the syntax tree into bytecode. Lua has a bytecode interpreter. I believe Python also uses a bytecode interpreter. Some versions of JavaScript interpreters use a bytecode interpreter. I believe Safari's JavaScript core actually recently just rewrote their bytecode interpreter. The purpose of bytecode is, you'll notice that in Ink's interpreter, whenever we run any bit of Ink code, the Go interpreter has to go in and figure out the syntax tree, which if the syntax tree is really complicated, can be fairly slow and a complex process. So a bytecode is usually a much smaller set of instructions that are much more rudimentary, that can still be that is a bridge between what the computer executes and what the syntax tree itself says. So bytecode instructions may be most interpreters are stack machines, which means it pretends the computer just has one giant stack of numbers. So a possible bytecode instruction may be take the last two numbers, pop them off the stack, add them together, and then put them back on the stack. Or multiply them and put them back on the stack, or multiply it, return it, and then go back to the previous function call. These are much more primitive instructions, but because of that, they run much faster. And it is possible to take a syntax tree and turn it into just a list of bytecode instructions. It's one more step in the interpreter process, but it does mean that the actual interpreter can be either simpler or faster or both. So this is sort of an in-between between the Ink interpreter as it stands, which is fairly minimal, and like a production-ready interpreter for a production-ready language like Python or JavaScript. Java also actually works in a fairly similar way. So yeah, that is the basics of how I made the programming language. An interesting thing to look at before we take off at the end, maybe the language specification. So when I first started planning out the language, I couldn't just immediately start writing the interpreter because I had to figure out how the language was going to look in the beginning. So there were two things that I did to try to figure out how the language was going to look. One was I wrote a couple sample programs. I believe the first program that I ever wrote was a Hello World, which is this. Like, this is the very first Ink program that I ever executed, then it ran on the interpreter, and I was like, wow, it actually works. It has all the basic aspects of an Ink program, like strings and function calls, and they're called in different ways. So I had this to work off of, but I still wanted like a canonical reference of what the language was supposed to look like and behave like. So that's why the specification exists. This is the Ink language specification. It's fairly informal. It's much more informal compared to like the JavaScript language specification or the Python specification, but it's like enough to write an interpreter. One interesting bit of this is where I outlined the syntax. This is a particular kind of popular notation for describing a language syntax. I believe there is a name for it that I've forgotten currently, but it's fairly easy to kind of reason through. So for example, that's actually incorrect. I don't know what that's doing there. For example, a binary expression is an atom or an expression, binary operator, and another atom or binary expression. So like 2 plus 3. An object literal is a left brace, then a bunch of object entries, and then right brace. An object entry is like a key, colon, a value, things like that. So you can see actually how this pretty directly translates into the parser. So if you like parse object. Wow, I can't figure out where I wrote this. Okay, so here, the object literal is really the only thing that actually begins with the left brace. So when we see a left brace, we automatically know that, the next thing that needs to be coming is a bunch of object entries. So like we make a list of object entries, and then we like find the entries and then we put them into it. So having this like pretty rigorous and specific grammar definition actually helped a lot in writing the parser pretty quickly. This is a list of like all the valid binary operations and things like that. And then we also have a bunch of types. A language needs types. These are all the valid types in Ink. There's a number, there's a string, there's a boolean, there's a null, there's an object and a list, which are both called composites. If you know Lua, it's like Lua tables. And there's a function. These are all of the valid types. Everything else just falls into one of these categories. And having all the types outlined makes it a lot easier to write the actual executor, evaluator part of the program, because I know that I've covered all of the possible types that an input could be. And there's a bit of like concurrency, which I might talk about later, and then built-in functions. But that is the language specification. Is everyone else here from the Link in the Hat Club? Well, there are four other people. I think they're both from Twitter, actually. But I did post a Link to Hat Club. I think I want to go out with a bang. So I'm just going to run one of my favorite programs that I ever wrote in Ink, which is a Mandelbrot set generator. Mandelbrot set is a fractal, and they have it generates pretty images. This is written entirely in ink, and it's interpreted by the interpreter that we just saw. When we run this program, it's just nothing more than that interpreter running on this text file. So if we run ink on samples Mandelbrot, and let's make it verbose. Why not? Okay. So it's rendering the image. While it's doing that, we can study sort of what the interpreter saw. Wow, that's a lot of stuff. We can study what the interpreter saw when it looked at the program. Like, we ran this thing, and it first just saw a bunch of tokens, all kinds of tokens. And then it parsed that into, like here is like a parsed tree of tokens, and then more tokenization, more parsing, more tokenization, more parsing. And like this is an instance of like a really big, really complex syntax tree. In the end, the image is generated. Let's open it. Ta-da! That's very low resolution, but it is a fairly complex thing to generate. So yeah, that is ink. Hopefully this was sort of interesting and hopefully not too complicated. If there are any questions, you can tweet at me at the Cephist or comment. I guess I don't really check comments, but that's fine. Or find me in Hack Club if you are from Hack Club. Otherwise, you can look at all of this on GitHub. Wow, I have too many tabs open. There's a bunch of sample code, there's a bunch of instructions, and like a little bit of explanation on how it works. So hopefully that's kind of interesting. Hey, I have a new GitHub star. But yeah, that's ink. Thank you for watching the live stream. Hopefully this was kind of interesting. And maybe I'll do more of these. See ya.